This video will be about proteins and their structure. So far, we've been focused on how amino acids make up dipeptides and tripeptides and even bigger polypeptides. So what's a polypeptide? So polypeptides, that's really a term for having, usually people say 2 to about 39 amino acids. I mean, again, if we have 2, we call it a dipeptide. If we have 3, we call it a tripeptide. But, up to like 39 or so amino acids, people call polypeptides. Proteins then are polymers of 40 plus amino acids. I mean, these are lots of amino acids end to end to end with peptide bonds holding them together. So the big idea here is that the 3D shape of proteins determines their function. So we have a picture of a slab of meat here, just to kind of remind us of our protein sources, or things like meat and dairy. The primary structure of proteins is the sequence of a chain of amino acids, and each amino acid is represented as a little circle here. So instead of writing out the whole structure, sometimes we abbreviate that whole complex structure we've been talking about as just a circle for the amino acid. And then we connect them end to end like a little amino acid snake, essentially, to show that proteins are a polymer of these amino acids. And then if we go, next is secondary protein structure. Secondary protein structure occurs when the sequence of amino acids are linked by hydrogen bonds. So secondary protein structures are things like pleated sheets and alpha helix. They give rise to the overall shape of the protein. Tertiary protein structure occurs when certain attractions are present between the alpha helices and between the pleated sheets. So tertiary protein structure gives rise to overall shape as well. It just results from group interactions, like R group interactions. And then lastly, we have quaternary protein structure, which is protein structure consisting of more than one amino acid chain. So this results from interactions between 2 or more peptide chains. Insulin is an example of, a protein or a peptide that has, takes advantage of or has quaternary structure. Not all proteins actually have quaternary structure, but we have some cool examples like insulin that do. Okay, so more on protein structure. So again, primary structure, sometimes we abbreviate that with our 1 degree. We don't really say it that way, but we abbreviate it that way. Primary structure is really what's the sequence, the order, the sequence or the order of amino acids, AA always for amino acids, in a protein. So what's the sequence or the order that the amino acids are going to be in? Here we're using a 3-letter code. So we're going to use a 3-letter code for each amino acid. In the peptide backbone. What do I mean by that? Well, the sequence shows ALA for alanine, LEU for leucine, and we could just go on, SER for serine, but they just go on like that with their 3-letter abbreviations, GLU, GLU, HIS, ALA, GLN, ILE, SER, TYR, ALA, SER, GLU, GLU. So we can repeat some of the amino acids. Sometimes each one gets circled so that each one, rather than showing its complex amino acid structure, we actually kind of end up almost looking like, I don't know, like a little worm. or a little, chain or necklace, if you will, where each bead is a circular or spherical protein. So it's just a way of really abbreviating. So primary structure is the amino acid sequence. What order are the amino acids going in? Like alanine and then leucine. What is their actual order? Secondary structure and tertiary structure, so that second and third degree structure, they really lead to the overall shape of the protein. They really play a big role in overall shape. Secondary structure really results from hydrogen bonding. So I think I'll continue that over here. So secondary structure is really from H bonds between, NH2s and COOHs, so between amines and carboxylic acids in the main chain. So that's where secondary structure comes from. So we think of that alpha helix, for example, and we give it the abbreviation alpha, and we think of that beta pleated sheet. We really think of that alpha helix as held together by hydrogen bonds or caused by hydrogen bonds. And then that tertiary structure, here we show it as a folded polypeptide chain. That tertiary structure really results from R group interactions. So remember that the amino acid, they each have an R group. So that tertiary results from R group interactions. What do I mean by that? Well, R groups on amino acids from one alpha helix can interact with those of another. And so when we're showing the tertiary structure, we're really showing the alpha helix, inside of this tube that is now woven and twisted as a whole tube. So here we've got this tube that's woven and twisted and turning, and then within that tube is our alpha helix held together by hydrogen bonds. What makes this tube, kind of woven and twisted on itself? Well, that would be interactions from R groups. So, from those side chains, essentially, on the molecule, on the protein itself. Okay. And then, I was going to tell a little bit about quaternary structure. Quaternary structure doesn't really have a picture per se here, and I'm out of room, so maybe I'll just erase and I'll just kind of add that. You could add it to the bottom of your notes. But what about what we might abbreviate as 4-degree or quaternary structure? Quaternary structure is really from interactions between 2 or more peptide chains. So let's just squeeze that in here. Results from interactions between 2 or more peptide chains. Not all proteins have quaternary structure, but a classic example of something that does have quaternary structure where it's really important is insulin. It's a great example of where quaternary structure is important. So not all proteins have it, but when it does, it's about, one peptide chain interacting with the next one. So again, primary structure is about the order of the amino acids. Secondary structure is things like our alpha helix and our beta pleated sheet. Those are due to hydrogen bonds, between the hydrogen bonds between NH2s and COOHs in that main chain. And then tertiary structure is due to R groups on the chain interacting with R groups. And then quaternary structure is like one peptide chain interacting with a whole another peptide chain. So interactions between two or more chains. So let's talk a little bit about proteins actually denaturing. So what is denaturing? Denaturing is really about loss um, of some of that structure. Really about loss of your secondary, your quaternary, or your tertiary structure. It's not about loss of your primary structure, because breaking apart the amino acids, that was amino acid hydrolysis. That was really loss of primary structures when we talked about hydrolysis. This would be loss of, shape and function of the protein. So loss of shape and function of the protein. It really, in denaturing, the protein gets unfolded. Kind of think of it as really unraveling. It gets all unfolded. How does this happen? Well, let's think about it. How to denature a protein. What are some of the common ways that we can denature a protein? Heat. I think of a denatured protein example as a cooked egg, right? We're heating that and cooking it to denature that protein. Acids or basic environments can denature proteins. Heavy metals. Heavy metal can denature a protein. Some organic solutions can denature proteins. And then we have to be really careful with proteins, because even agitation in the lab, shaking, can actually denature proteins too. So it requires quite a bit of care. So here we've got a picture of an alpha helix. And this would, is an example of secondary structure, right? Here are our hydrogen bonds. So we've got this like almost ribbon shape, right? Curly Q on itself. And, where one row kind of curly Qs or connects to the next, that would be an example of a hydrogen bond that's sort of holding the alpha helix together. And so in denaturing, we lose some of that. Look how the ribbon sort of becomes flattened or unwound, or it just kind of goes straight. And so now we have this really random structure protein strand. The ribbon is just kind of flat and falling everywhere. So notice in the denaturing process that we've kept, the order of the proteins. Like we haven't, if this were a bunch of circles, we've kept them all connected. There's no breaking of the chain itself. So the primary structure is fine. The primary structure, the peptide bonds are intact. Primary structure, the peptide bonds. Primary structure is not changed in denaturing. That can only be broken in hydrolysis. Okay, so we denature proteins, we sort of unfold their shape with heat or acid or base or a heavy metal or an organic solution, or by agitating or shaking it. and then it really loses its secondary or tertiary or quaternary structure. Classic example is that alpha helix, which is that secondary structure from hydrogen bonding, gets all unfolded or unraveled, and the protein gets really denatured because of that. And so it has like a real random shape where the ribbon, if you want to think of it that way, is just kind of floating around everywhere instead of in this nice, neat, curly Q.